Good afternoon, everyone. I'm Picinini Freitas. I'm a postdoc at the University of Montreal, and I'm going to present today with Dr. Douwes-Schultz. He's a PhD student at Dengue University. The title of our presentation is a Bayesian Markov-switching space-time model for studying the first Zika epidemic in Colombia. So this is a joint work with Alexandra Schmidt and Mabel Caraballi and Kate Sinzer. Oh no, yeah, I have, okay. Anyways, Zika is a disease like dengue and chikungunya that is transmitted to humans by the bite of infected Aedes mosquitoes, especially Aedes aegypti. And these mosquitoes, they are climate sensitive, with temperature impacting their life cycle and also their activity. And rain is also important for them because they lay their eggs in small collections of water. Aedes aegypti, they are very adapted to urban settings. So poor basic sanitation, poor basic conditions, basic sanitation, living conditions, and high population density favor the presence of these mosquitoes because they can more easily find places to breed and to feed. So because these mosquitoes, they are affected by these factors, the Zika spatiotemporal distribution will also be associated with these characteristics. So Colombia has been historically affected with dengue. The first Zika cases in the country were registered in August 2015. And in a previous work, we identified the Southwest region as an important region for Aedes-borne diseases. So we identified it as a potential site of entry and dispersion of both Zika and chikungunya. So in the map at the top, we have the Zika spread in the country. And the yellow arrows represent the first registered cases, and we can see a yellow arrow in Cali, where it is located in the Southwest region and is one of the biggest cities in the country in terms of population. Then we also identified, I'm sorry, we also identify high-risk clusters for Zika, dengue, and chikungunya in this region. So the map in the bottom, we have the identified clusters for Zika. And the area in dark red represents the most likely cluster, which is the cluster with the strongest statistical evidence. And it is located in the Southwest region. So our objective is to study the first Zika epidemic in Colombia and explore how environmental and sociodemographic factors are associated with the emergence, transmission intensity, and persistence of the disease. For now, we focus on the Southwest region and selected 168 municipalities from 4 departments are shown here in the map. So they are Cauca, Huila, Tolima, and Valle del Cauca, where Cali is located. And we obtained surveillance data. So there were around 27,000 Zika cases in this study area between epidemiological weeks 26 of 2015 and 39 of 2016 that comprehends more or less the period of the first Zika epidemic in the country. And the maps in the top, they show the cumulative Zika cases and incidents for each municipality. And we can see a concentration of cases in Cali that's shown in the first map in black. And we can also see that there are a lot of municipalities that did not report any cases during the study period, depicted in gray, especially in Cauca department. And in the bottom, we have the distribution, the temporal distribution of cases and incidents for each department. So for covariates, we obtained sociodemographic data, the percentage of people with unsatisfied basic needs, which is an official index from the Administrative Department of Statistics of Colombia that is thought to capture and represent social vulnerabilities. And we also obtain population and calculate the population density by kilometer square. And we also obtain environmental data that was organized and made available by ICIHAJ and collaborators. So the NDVI that quantifies vegetation, the precipitation, and the temperature. So the maps, they show the mean values for the study period, and the graph shows the weekly precipitation and temperature for each department. And we can see that there is some spatial and temporal heterogeneity as well.
So we need a statistical model that can account for the long periods of Zika absence that we see in many of the areas. And we also need to be able to account for the imperfect detection of the disease. So we use this zero-state Markov-switching spatial temporal model that I've been sort of developing in my thesis. Now, with this model, we assume that the reported number of Zika cases in area I during time t is 0. If Zika is absent in area I during time t, and the reported cases follow a Poisson distribution with mean lambda it, if Zika is present in area I during time t. So here, SIT, that's a binary indicator for the presence or absence of Zika. So SIT is 1 if Zika is present, and SIT is 0 if Zika is absent. And we assume that these binary presence-absence indicators follow a non-homogeneous Markov chain within each area. And here we have the transition matrix for the Markov chain in area I. Now, P01IT, that's the probability that Zika goes from being absent at time t-1 to present at time t. So P01IT, that's the probability that Zika emerges in area I during time t. And P11IT, that's the probability Zika goes from being present to present. So P11IT is the probability that Zika persists in area I during time t. And we assume that both the probability of Zika emergence and the probability of Zika persistence can depend on a vector of space-time covariates through 2 logistic regressions. And this allows us to investigate associations between various environmental or socioeconomic factors and Zika emergence and Zika persistence. So for lambda IT, we use what's called an endemic epidemic model. So this composes the expected incidence into an epidemic component that's meant to account for transmission from the previous cases. Although as we're modeling the reported cases, it's also accounting for some reporting effects as well. And then we have an endemic component, which accounts for other contributions to incidence, such as imported infections or environmental reservoirs, things of that nature. So we use a log linear model for the transmission intensity, so it can depend on a random intercept to account for between area differences. And then it can also depend on a vector of space-time covariates. So the transmission of Zika could vary with rainfall or temperature, for example. And for the endemic component, we just assume it follows a random intercept, because in my experience with these models, the endemic component does not account for a lot of the incidents. So to fit the model, we use the R package Nimble using MC methods, which is a Bayesian technique. And if you're interested in more details, I can refer you to the paper on that. So now I'll go over some of the results. So I'll start with the results for the emergence of Zika. So the only covariate that we found that had a significant association with Zika emergence was temperature. So we found that an increase in maximum temperature lagged by 1 week that was associated with an increase in the odds of Zika emerging. So essentially, Zika emerged sooner in warmer areas compared to colder areas. Now for the transmission intensity, we found that lagged increases in both rainfall and maximum temperature, that was associated with an increase in the transmission of Zika. And we found that an increase in population, an increase in NDVI was associated with a decrease in the transmission intensity. So that means that urban areas had more transmission of Zika compared to rural areas. So for the persistence of Zika, we only found one covariate, population density, which had a significant association with Zika persistence. So we found that an increase in population density was associated with an increase in the odds of Zika persisting. So that means Zika was more likely to persist in population dense areas. And here we have the fit of the model in 4 areas. So as you can see from the top graphs, the red dots, that's the actual Zika cases, and the black line in shaded areas is the fit of the model. So as you can see, in some of the areas, the credible intervals are a little bit narrow. We are working on a negative binomial model, which will widen those a bit. Now, in the bottom graphs, what you're looking at is the posterior probability that Zika is present. So it's the posterior mean of those binary SIT variables that I was talking about earlier. Those are variables in the model. We estimate them like we would any other variable. And you can kind of look at the second area. I can try to explain what's going on. So if you look at the second area here, it's saying that Zika was absent initially, and it became present for a time, then it went extinct likely at the very end. And one thing you might notice is that zeros in this model, zeros can be assigned to periods of presence. So the model doesn't necessarily think that Zika is absent for those zeros. It could be undetected.
Okay, so now I think Can you put play on the video? Okay, thank you. So now it's a video of the probability of disease presence in the left, and here is the reported cases for comparison. And what we can see is that the probability of disease presence increases before cases are actually being reported. And as time goes by, some municipalities stop registering cases, but the probability of disease presence remains higher than was in the beginning of the study period. So as conclusions, our results indicate that environmental factors were more related to the emergence and to the transmission intensity of Zika in selected municipalities of Colombia, while the population density was the only factor that was associated with disease persistence. The increase in the probability of disease presence weeks before the first recorded cases indicates that Zika may have circulated for a while undetected, and may also indicate municipalities that have reporting issues. And currently we are working on inclusion of other covariates. We are including considering a negative binomial distribution, considering 3-state models, and the department varying intercepts and extension to the whole country. This work is supported by a grant from the Canadian Institutes of Health Research, and Dirk and Alexander Schmidt are sponsored by grants from IVADO and the Natural Sciences and Engineering Research Council of Canada. Thank you for your attention. We'll be happy to answer any questions. And if you scan the QR code, you can have the references and our contact details. Thank you.
So just to start with the question, maybe just one, because in your regression, so you were mentioning something like the significant variable you got was the population density, right? So I was wondering if it's not what we usually observe, which is usually you get more disease where you get more doctors. So it doesn't mean that doctors bring the disease, just that this is where people get tested. So is it something like that in this area, or is it just because you observe more people getting tested in dense areas that in far away from the cities?
In that case, we're talking about reported cases that not necessarily are tested, but they are
Tested, yeah. So
what?
You need to report something.
They are reported, yes. But we used the municipality of residence, not where people were seeking care necessarily. So this could be it, but usually infectious disease, this is a common result, right? That the population density has an association with the transmission, but we found it interesting that it wasn't associated with the transmission intensity, only with the persistence.
Okay. Any other questions from the room? Okay, so thanks again for this talk.